All right, so my name is Tang Liu. I'm from Catholic University. So my talk is cross-layer optimization for massive MIMO and millimeter wave networks. We know, several advanced radio technologies adopted or considered by 5G and future networks, like massive MIMO or non-orthogonal multiple access and millimeter wave communications, which with much wider bandwidth. So those techniques can achieve much higher capacity gains, but also introduce some new advantage, new challenge for the upper layer algorithm and the protocol design. So basically, how to design the higher layer algorithm and the protocols to leverage those new physical layer capabilities for cross-layer optimization. So we studied several cross-layer schemes and really want to evaluate them on the Cosmo testbed. So the first scheme we are considering is this massive MIMO beam power allocation and scheduling. So we know for the massive MIMO, right, a base station can send K streams to a set of K users simultaneously on the same frequency band. So consider some traditional beam power allocation and transmission scheduling algorithm. Typically, we assume the user traffic and channel conditions are known through some estimation. Then we can maximize the total throughput, and more similar to these water filling algorithms, which we call this one-shot optimization at the current time slot, or we can also achieve some fairness. So, but for many mobile scenarios, we know that the statistics of user packet arrival or the channel state distributions may not be known a priori, and also is time varying. So basically, if we can cast this massive MIMO beam power allocation and scheduling as an online optimization problem, so instead one-shot static optimization, so it's more reasonable or compiling. For example, if we know this user gonna get into the building in the next time slot, so we can allocate more power and transmit more data before his channel become bad, right? So then we can use this deep reinforcement learning algorithm, which allow us to learn this network dynamics that take into consideration like a longer term factors, and that basically optimize this long-term system performance. So we design some algorithm. Basically, we can formulate this problem as a Markov decision process to optimize a composite performance metric, including the delay, loss, and power efficiency. And then we can design some deep reinforcement learning algorithm, so which we use double deep Q network-based algorithm to learn this network state transition statistics and achieve the optimal power allocation and scheduling policy. So we did some simulation. Basically, the simulation result can show this reinforcement learning-based algorithm outperform we call it the one-shot traditional optimization scheme, right? But testbed experiments really allow us to study the trade-offs between the performance and the complexity and overhead in a more realistic setting. So if we consider the testbed, so what is desired feature the testbed can support? Of course, we need some interface to expose the 5 conditions, like a CSI, the packet loss for each user, and also we need some interface. We can fine control the transmit power for each these MIMO beams. Also, we need to measure the packet arrival statistics and the queue state and maintain those information then for the learning purpose. So also we need some enough computation power and memory for the deep learning algorithms. Then we also can extend this very simple single hop, single cell optimization scheme to a more complex topology. For example, we consider the cloud run, right? So then with massive MIMO as the front hop to connect small cells, then we can jointly optimize this massive MIMO power allocation for the front hop, and then this UE and small cell association. And if we consider the small cell, just use the traditional OFDM-A type of access. So how can we allocate the sub-channel resource and transmission scheduling in the small cells? So once again, we can use this simpler one-shot throughput optimization scheme. So by assuming we can estimate users' packet arrival and estimate the channel state statistics. Of course, we can also develop more intelligent algorithms like reinforcement learning algorithm than to consider the non-stationary network statistics. So since we have multiple hubs and the components, the elements need to talk to each other, we also need to support this customized mic-level control signaling for the experiments. So another setting, we can go one step further, become more complex. We can consider there are some small cell access point. Those can be the secondary network. So it can cooperatively relay traffic for some legacy macro cell users while concurrently accessing the macro cell spectrum to transmit their own data by using MIMO and NOMA techniques. So this can create a win-win situation. Basically, the throughput of the macro cell users can be significantly increasing because of relay, and also it's the small cell, and those small cell AP are able to use the spectrum to serve their own users. So we can design some algorithm and protocol for the relay selection and the resource allocation and the transmission scheduling by leveraging this MIMO technique and NOMA for this joint performance optimization. So here we can use different techniques like game theory or matching techniques or some machine learning techniques. So in summary, so for the cross-layer design, in terms of network topology, we can have a simpler network topology, for example, the single hop and massive MIMO power allocation and scheduling. Or we can have more complex two-hop and cloud run, the joint optimization, or even more complex many-to-many cooperative relaying, right? From algorithm point of view, we can have this more traditional optimization algorithm and try to achieve the maximum throughput or minimum delay or achieve some kind of fairness. But we can also have more this machine learning or deep learning based more intelligent algorithm to power the radio. So basically, no matter what kind of algorithm we are using, what type of topology, from experiment point of view, so we need to get some information from the physical layer. So basically, we need to have the interface to expose the phi state, basically like CSI, the packet loss, etc. Then we also need to have an interface so which allow us to control the phi behaviors. For example, for the MIMO, so we want to control the per beam-based power, and also we can schedule the packet transmission. If we have more complex machine learning-based algorithm, we also need to measure or maintain certain network states. So including the packet arrival statistics, the queue states, and also we need to get some channel state to maintain it and learn and to get better results. So in terms of the signaling at the mic level or even in the phi level, so it would be nice to be flexible, allow us, to change some message format and to add in some customized message, especially for the more complex network topologies. Also, for each of node, probably we need some computation power and memory still, especially if we want to do some deep reinforcement learning, so type of algorithms. So I keep my talk is short, and then we can maybe have some question or discussions, and in terms of the Cosmos testbed and how could we support this more advanced or more intelligent cross-layer design.